So let V vector spaces over some field F, and let B consisting of vectors V1 until Vn be the basis of vector space V, and V1 arbitrary, but of course all of them are in W, in the vector space. And then there exists, so if we have the things so far, then there exists exactly one F from V to W, such that for each I, we have F of V sub I equals W sub I. For all I ranging from, or we can say 1 till N. All right. So let's now prove this. This is a long statement, but it can be proven. So the first step would be talking about uniqueness. So first thing is uniqueness. Well, for uniqueness, let's suppose that we have, of course, this linear map and the stuff so far. So this stuff that was just mentioned, and let some vector x inside a vector space V arbitrary B is basis, now let's refer, of the vector space V, and that implies there exists unique C1 until Cn inside the field we're using, such that x equals C1 V1 plus, and then until Cn Vn. So a linear combination of the V1 till Vn, each with the scalar C1 till Cn, respectively. And by F's linearity, because it's a linear map, so it has linearity, we have the following. F of x, so we're either talking about x or x with the arrow, it doesn't matter, the notation is personal choice how to write it. So F of x would be actually putting x in this form inside it, which if we skip a few steps, we actually realize that that will end up as the following. C1 times F of V1 plus until Cn times F of Vn. Because we would first put the x inside here in this form and then expand it out using the properties of a linear map. And so with that, we got quite far because we can realize this is Wi, or W1, this is Wn, and all the ones between. So this is C1 times W1 plus until Cn times Wn. All right. And hereby Fx is determined completely for every x inside the vector space V. So that's uniqueness. And let's now talk about another step that would be existence. So let's go to this part. So again, define this V to W linear map, and for any x inside the vector space V, write in B. So in relation to the basis B, we can write x equaling C1 V1 until Cn Vn, and f of x is then defined as C1 V1 Cn W1 until Cn Wn. And it is well defined. The reason is C1 till Cn are unique. That's the reason. And f of x doesn't depend on any choice. So, because of these two reasons. We can just say this is well defined. Well, for every I, we have f of vi equaling wi, which was already mentioned. And we can realize that vi has coordinates 0, then skipping many places, 1, and then skipping many places until 0. This order from 0, and then a few places empty 1, a few places empty, and then a 0. Let's now, in the end, also take care of linearity. So what we have here is we let xy be inside the vector space V and alpha inside the field, the underlying field. We can then write sigma from 1 until n ci vi and y equaling I from 1 until n, let's say ki vi. Then if we add them up, what we actually get is one sum from 1 until n. That is going to be ci plus ki times vi. And alpha times x would then be equal to I from 1 until n of alpha times ci times vi. All right. But by definition of f, we should realize that f of x plus y can be written as this sum. Just like this. Times wi right here. And we can again separate it out into I equals 1 until n, ci wi plus the same sum with a different constant here, which is f of x plus f of y. And also, we can take a shorthand. We can just realize f of alpha x. We can take the expressions that we just yielded a few moments ago and realize gradually that this is actually going to be equal to alpha times f of x. And so f is linear. So that's proven as well. And so let's now get to the conclusion. The conclusion would be there exists one and only one linear map f from the vector space V to W vector space such that f of Vi equals Wi. And that's for all I in the set 1 until n. The same like we said before, just this time described in a slightly different way, the same like saying for all I equaling 1 until n.